Hello class. This video is going to cover chi-square test. In order to introduce the chi-square test, we need to take one step back before we start moving forward. All of the tests that we've covered up until this point are what's known as parametric statistics, meaning that they make assumptions about the distributions that are being involved. And in particular, they assume that those distributions are typically normal within the population and that the dependent variable is either interval or ratio, so it's continuous in nature. The chi-square test does not make that assumption, so it doesn't have any assumptions or inferences about the population parameters. It can be used with any distribution and it can be used with categorical data, so nominal or ordinal data. Because of that, it has some advantages and there are situations where we can use it. And in fact, when we violate the assumptions that we've talked about in the previous test, so when our distribution's not normal, whenever our variables don't meet those criteria of being continuous in nature, or we really think the variables are more ordinal in nature, we don't have that interval level where there's this equal distance between each value, then it would be more appropriate to switch to non-parametric statistics. And there are actually a number of non-parametric statistics. So Mann-Whitney U is one that you can use in place of an independent samples t-test as an example. Kruskal-Wallis can be used in place of the ANOVA. And we're not going to go into all those, but when you violate those assumptions that we have for the independent samples t, dependent samples t, any of those different tests, it actually would be most appropriate to evaluate which of the non-parametric statistics, which of the alternatives would be better because of that assumption violation. So we're not going to delve into that too much, but just a reminder that those are all parametric statistics that we've covered up until this point, and the chi-square is a non-parametric statistic. There are two types of chi-square tests. There's the chi-square goodness of fit test. With the chi-square goodness of fit test, we're going to compare observed and expected frequencies for levels of a single categorical variable, or we could do it with multiple categorical variables that are observed together. And here, typically what we're doing is comparing a sample to a known population. So if we want to look at, does our sample represent the United States population in terms of ethnicity, we could look at the percentage of individuals that we have in each category, or the number of individuals, the frequency of individuals that are white, black, African American, or Asian, and we could go through each of those groups and then compare it to the general population for the United States. We're not going to go into that test in particular. The math behind it is basically the math behind the second type of test, which is the one we're going to focus on, the chi-square test of independence. The chi-square test of independence allows us to determine whether frequencies observed are different from the frequencies expected when we compare two categorical variables. In both cases, though, we're still thinking about deviations, except now, instead of our deviation being an individual score deviating from the mean, our deviation is the difference between the observed frequencies and the expected frequencies. And again, think about frequencies. We covered that earlier. Frequencies is just little n, right? The number of individuals in a cell. And then we'll talk about how to calculate expected frequencies in a moment. So as I mentioned, the chi-square test of independence, we are typically comparing two categorical variables. So an example of this would be if we wanted to look at the association, the relationship between ethnicity and socioeconomic status. With ethnicity, we have a categorical variable, Caucasian, Hispanic, African American. With economic status, we also have created a categorical variable above and below the poverty line. Now, we could look at economic status as the total amount of dollars that somebody earns. The thing with that is, if we really want to look at the impact of poverty, we now need to account for the number of family members, things like that. If we create a dichotomous variable, whether the individual, that household, falls above or below the poverty threshold, well, the poverty threshold moves so that for each child added, a certain number of dollars is added to what is considered to be the poverty threshold for that household. So we have these observed variables, and that's simply the counts. How many Caucasian individuals were above the poverty line, poverty threshold? And so we see that there were 60 of them. Now the next question is, what about those frequency expected? So we talked that there's this deviation, this difference between the frequency observed and the frequency expected. Frequency observed, you've done this before. It's just if you can count, you can do frequencies. That's really all it is. And then we have to count for each group. Do you fit those two criteria? If you are Caucasian and you're above the poverty line, you are counted for that group. If you are Caucasian and below the poverty line, you are counted for the other group. And so we just are doing conditional counts basically. In an earlier video, we did count if, for instance, in Excel, and that would work to help us do this. The alternative hypothesis is ultimately that the expected values and the observed values are not equal. So we're looking to see if they are equal, we would end up failing to reject the null hypothesis. And because of that, we would actually say that the data is consistent with the null hypothesis. When we go to calculate the frequency expected, the way that we're going to do that is we're going to take the row total, multiply it by the column total, and then divide by big N, divide by the total number of individuals that are in our sample. So looking at this data, for the first row above poverty line, there are 85 individuals. So if you take 60 plus 15 plus 10, 85 individuals are above the poverty line. And in fact, nationwide, the data is that about 85%, fortunately because I used 100 as my total, I can go back and forth between the raw number and the percent really easily. So 85% of the whole population is above the poverty line. So this does actually fit with the real data. I've made it up, but it's largely consistent with what you would find if you looked at the Bureau of Labor Statistics, for instance, of above or below the poverty line by ethnicity. I've also simplified it to only look at 3 categories, and of course there's more than that, but for the sake of this demonstration, it's easier to use a fewer number of categories. So I have Caucasian, Hispanic, African American, and I've excluded other categories like Native American and Asian just for simplicity. So we have the total for that row, the above poverty line. That's going to go in our row total. We're then going to multiply that by the column total. So the total for the first cell, for instance, that would be the column total for Caucasian. So we're going to say row total above the poverty line times column total Caucasian. So if those individuals were evenly distributed, so if 85% of the total Caucasians were above the poverty line, what number would we expect? And then we divide by the total number of individuals in the whole sample. That's 100. And so that tells us if there was an even distribution, right? If the expected frequency was equal to the observed frequency, then we should see that it would be 56.95. In fact, we see that there are 60 Caucasian individuals in that cell. And so the number of Caucasian individuals who are above the poverty line is a little bit higher than we would expect if there was actually an even distribution of poverty, for instance. So we're going to go ahead and put that in. A lot of the times you'll see this in parentheses to denote the observed value, not in parentheses. In parentheses, we have the expected value. And then you're going to do that for each individual cell. So for the cell Caucasian below poverty line, the row total for that is 15. The column total is still 67 because that's the total number of Caucasian individuals in our sample. So we would say 15 times 67, we still divide by 100, and that would give us that value. And then we would do the same thing for Hispanic. And Hispanic above the poverty line would be 85 times 19 divided by 100. Hispanic below the poverty line would be 15 times 19 divided by 100. And the 15 there is coming from the row total. I know there's also happens to be 15 Hispanic people above the poverty line, so don't let that throw you off. It's the row total times the column total. We go through, we do that for every single cell, and we end up finding that there's expected values are 56.95 for the Caucasian above the poverty line, 10.05 for Caucasian below the poverty line, 16.15 for Caucasian for Hispanic above the poverty line, 2.85 for Hispanic below the poverty line, and we go through and we do that for each person. If you add these up, so if you add the expected values across this top row, 56.95 plus 16.15, we add those together, we end up with 56 plus 16 is going to give us 66, 72, and then we have 72.95, we add 0.15, that gives us 73.1. 73.1 plus 11.9. So zero point 0.1 plus zero point 0.9 gives us 74. 74 plus 11 gives us 85. So we still have 85 people. What we've done is we've distributed those people to say, okay, if each group was equally represented above the poverty line, if there was the same percentage of people basically above the poverty line in each group. So 85% of the Caucasian people were above it, 85% of Hispanic people were above it, 85% of African American people were above it. What value would we expect under that condition? Well, we would expect that 56.95% of the Caucasian people, or 56.95 people, again, I can go back and forth easily because I have 100 people, would be above that threshold. 16.15 Hispanic would be above, and 11.9 African American would be above. Now, we are interested in the deviations, so frequency observed minus frequency expected. And in fact, when you look at the chi-square obtained, we see that that is the numerator, is that deviation, that difference between the expected value and the observed value. And when we look at Caucasian, we see that that value is above the expected value. So it may be, if we find this is significant, that there are more Caucasian individuals above the poverty line than we would expect if they were equally distributed. That would suggest, if that happens and there is a difference, that there's an association. That in this case, perhaps white people are more likely to be above the poverty line than one would expect. There's an association between poverty and ethnicity, and I don't think you would be surprised to find that. By contrast, when we look at Hispanic, we see that the number of individuals above the poverty line is slightly less than, so it's 15 compared to 16.15. So if 85% of them are 80, if 85% of the Hispanic individuals, the 19 individuals that were Hispanic, were above the poverty line, then we would find that it is 16.15. But the observed value is actually below that, which would suggest that maybe they're below the poverty line more than we would expect if it was evenly distributed, if the frequency observed equaled the frequency expected. So we're going to go through and we're going to have to do this calculation for each cell. So before, we often did our calculations for each individual, and then we had to add them together for square deviations, for instance. We're kind of doing that same process, but now our focus is on each cell. Frequency observed minus frequency expected squared, because we have to deal with the fact that some are positive, some are negative. And then we're going to divide by frequency expected to put it back into terms of the number of individuals. So we calculate the difference for the first cell, 60 minus 56.95, square it, divide by 56.95. We do this for the second cell, 7, the observed value, minus 10.05, the expected value. Square that difference, divide by 10.05, the expected value. We do that for each cell, so 15 minus 16.15, square that, divide by 16.15. For the next Hispanic cell, which we're kind of skipping there, it's in those ellipses, we would do 4 minus 2.85, square it, divide by 2.85. Then we'd do 10 minus 11.9, square it, divide by 11.9. And then we get to the last, which is where I have added it in. I've actually written it out again. And that would be 4 minus 2.1. Square that difference, divide by the expected value of 2.1. And we find that when we do that, our obtained chi-square is 3.6573. Now the question is that significant? So same way that we've done it with the f-test, the t-test, the z-test, we take our obtained value, compare it to the critical value. And so in Blackboard, there is a critical value sheet. I pulled it from a different source, so it's from a source called Privateera. B7 is the table. And so if we look at that table, we're going to need to know the degrees of freedom because as with the table for the t-test, as with the table for the ANOVA for the F table, we need to know degrees of freedom so that we know the appropriate critical values. Degrees of freedom for chi-square is relatively easy. So it's k minus 1 for each of our grouping variables. So we have ethnicity and we have socioeconomic status. So we're going to have ethnicity has 3 groups. So we'll have 3 minus 1 for that variable. And then SES, we have 2 groups. So it's going to be 2 minus 1 for that variable. And when we do that, we find that our total degrees of freedom is 2. 3 minus 1 times 2 minus 1. So 2 times 1 gives us 2. And then we can use that information with the table. And I've taken an image of the top of that table, but that's where this is coming from, is that table B7, which is in Blackboard. And when you look at degrees of freedom, assuming that our alpha level is 0.05, I haven't said anything, so we'll assume that that's what it is. Degrees of freedom being 2, alpha level being 0.05, we find that the critical value is 5.99. We don't pass that. We are not more extreme than that. So chi-square, like F, goes in one direction. So we're only interested in, do we exceed? Are we greater than that critical value? In this case, we're not, which would suggest that maybe there's not a difference. Maybe there's not an association between poverty and ethnicity. Now, we have enough data to know that there is. So that raises the other question of, well, if there is a difference, why are we not seeing it? Chi-square is particularly susceptible to sample size. So as sample size gets bigger, all things being equal, chi-square will get bigger. And even more so than the t-test and the f-test, it's basically proportional to. So if you double the sample size, you'll basically double your chi-square. Not exactly, it's a rough estimate, but if you have 200 people, you actually would end up with a little over, what would that be? 3.6573 times 2 would be about 7.3, give or take, something like that. And so if you double the sample size, you should see that the chi-square also doubles. And we'll actually show you that with the in-class example, where we go through, we do this with 100 people, we also do it with 200. One way to deal with the impact that sample size has on chi-square is effect sizes, and Cramer's V is the effect size that's normally reported with chi-square. The formula for Cramer's V is the chi-square divided by n plus the degrees of freedom smaller, and degrees of freedom smaller we literally just mean between our two grouping variables, where we have k minus 1 for the first one, k minus 1 for the second one, which of those values is smaller? So in this case, we have ethnicity where it's 3 minus 1, we have poverty level where it's 2 minus 1, and so our two degrees of freedom are 2 or 1. The smaller of those is 1. So we're going to take that 3.6573, we're going to then divide that by n. In this case, the total sample size is 100 plus 1. And when we do that, we find that Cramer's V is equal to 0.1903. If you compare this to SPSS, you'll find that the value is just a little bit different. I can't remember what the value is off the top of my head. It's 0.19, and then at the thousandths place, or I guess the 10,000ths place, you'll see that it's a little bit different. So I want to say it's like 0.1902 or 0.1908. The reason is there are more complicated formulas for Cramer's V. We're going to stick with the simple formula. It'll still give you a good solid estimate. Now, the other side is in deciding if Cramer's V is large or small, we then have to actually keep in mind degrees of freedom. And you can look in your book to find, is it large or small based on the total degrees of freedom that I have. And there's some charts that would help you with that. In this case, though, we have a moderate Cramer's V. And so that would suggest that there probably is a relationship, there is an association between ethnicity and SES. We just didn't have an adequate sample size in order to see that. In the second part of the video, as I mentioned, we're going to go through this with 100. We're going to go through this in Excel with 200, and you'll see that the critical value stays the same because we still have the same number of groups. We have 3 groups for ethnicity, we have 2 groups for SES, so the critical value is always going to be 5.99, assuming the degrees of freedom is the same. But the obtained chi-square will be considerably larger whenever your n is larger.